Hello and welcome to the SPIR-V backend talk. The SPIR-V backend has become an official target and a tool to produce SPIR-V in SQL. So we plan to expand our presence in real-life applications, including deep learning workloads, and would love to see also another implementation of SQL, which is adaptive CPP, using the backend. Our general goal is quality, also performance and functional improvements, of course. So let's discuss changes and steps taken to achieve those important milestones. This talk covers technical and community aspects of the SPIR-V backend. We join different topics, and this reflects the complexity of the project that bridges LLVM and SPIR-V with heterogeneous computing. It's not a single message to convey, but a set of stories about challenges, solutions, and integrations. From our side, the project scope and driving force is heterogeneous computing in general, and SQL as one of applications, but not as a restriction of any kind. In this domain, the compilation process is complex and complicated, and a unified representation of code is required to materialize compute kernels across various backend APIs, targeting various hardware. A key challenge is deciding what gets converted and when, as code moves from backend independent IR to device-specific binaries. Here, SPIR-V comes to the rescue as an abstraction that hides details of vendor-specific instruction sets and languages. SPIR-V and its native LLVM backend as the combination of a format and transformation step is our answer to this complexity. SPIR-V is a cross-vendor portable IR for compute and graphics, and the SPIR-V backend is a previously missing link in the LLVM toolchain. We have the Khronos Translator to generate SPIR-V, but it adds complexity and dependencies, being non-upstreamable. So applications get additional dependency on the external tool. Our native backend removes this barrier, offering tighter integration and better maintainability. Supporting SQL has been a driving force behind development, but HLSL and Vulkan equally benefit from the compute improvements as maturity of our project is increasing, getting better for real-world workloads. Bringing SPIR-V directly into LLVM makes toolchains simpler and gives vendor more incentive to build on top of it. It's no longer just about compatibility, it's about efficiency and long-term sustainability across our toolchains. The SPIR-V backend is an intersection of interests, and the implementation is to coordinate involved actors and cases. Compute has high semantic expectations, SPIR-V instructions are well-defined, and the flow of meaning from source to target must be preserved precisely. This is challenging, having so many different users of SPIR-V in the role of portable IR. They are runtime environments, frontends, backends, add reverse translation from SPIR-V back to LLVM IR as part of hardware drivers implemented by Khronos Translator. Khronos Translator may struggle with unexpected and backend-specific patterns. LLVM tools and concepts alone also are not enough to fully capture rich SPIR-V semantics, requiring more effort. So now, if you connect all involved actors and cases, you see an intricate network of this crossroad. Shader in Vulkan and kernel in OpenCL and SQL may overlap in functionality, creating implicit dependencies and restrictions from runtimes that guard against unsupported SPIR-V capabilities. This may be eliminated in future, but until then, the backend is to manage this dichotomy, implementing shared core for kernel and shader, and relying on environmental checks to branch between these models to ensure correctness across different targets. One of backend missions is to clarify ambiguities in the SPIR-V specification. We have one recent example. It's how the compute flavor used image read-write instructions. They depended on shader capabilities, but might be used in compute with the unknown image format. This unnecessary coupling caused errors in compute workloads with images, and the SPIR-V backend helped the specification to evolve, documenting this behavior in the kernel context. Another major issue is runtimes against SPIR-V pointer types. The key word is fragility. Runtimes rely on SPIR-V types while frontends and optimizers may generate patterns that disrupt type tracking. Correct type inference is essential, but not always possible. There is no guidance in specs on how frontends are to create IR or intrinsics to finally map it to SPIR-V, and a frontend solves the problem on its own, which may lead to inconsistency. Again, recent example is a frontend packing byte-sized bools into a vector of 32 bits against the SPIR-V regarding a bool as having no bit pattern whatsoever. So while semantic consistency is the goal, the path to get there may be unclear and fragile. SPIR-V has a hierarchical type system and most instructions are typed. The backend runs a module path that scans IR for known patterns, uncovering dependencies and deducing types, and avoiding relying on name handling. To encode types and relations, type inference emits internal intrinsics. Type inference is complicated. Here we list draft steps to infer types in the backend. We analyze bodies of functions, maintain a work list of incomplete types, allowing delays in deductions until the entire model is analyzed. Get element pointer is fixed early. Function parameters are processed based on headers and call sites. There is a forward traversal to use operands to infer result types, and a backward traversal to update or refine operand types. Here you see examples of how the backend reasons in the forward traversal about type dependencies in IR. In addition to rules, there is a space for educated guesses, sometimes like in phi node with values of different types. There is also some prior knowledge about well-known functions encoded in the path, like pointer type conversions between address spaces, implying equivalence between argument and result types. The backward traversal infers operand types from results and makes sure we generate consistent types across the model. We build a pointer typecast in place and propagate changes further to affected operands users. In addition to reasoning about IR, we use semantics of well-known built-in opcodes. Finally, we check function call sites and finalize incomplete types. This is also the moment to save the function pointer extensions from the IR translator cleanup. Continuous helpers propagate changes with eventual insertion of pointer type conversions for instructions to remain valid, and patch LLVM types when needed. At the moment, the only case is one element vector case. Type inference is not always feasible in a well-formatted way when frontend doesn't generate enough meaning. Some SPIR instructions do not have corresponding LLVM instructions on intrinsics, like op group async copy. A frontend uses a built-in to encode this opcode that copies between pointers given number of elements. And that's the problem. Number of bytes would be more in the spirit of SPIR-V than number of elements. If we can't guess the pointer type, the opcode just will not work. So now imagine the call to the built-in as inserted into this slide without any helpful relations between pointers and IR to help deduct the types. This is exactly what we want to avoid in general, because it is dangerous to rely on mangling. But in this case, we just use pointer types as encoded in mangling. It would be nice, of course, to reformulate the opcode itself in terms of bytes, but it's too late to change. Feasible options are either the untyped pointer extensions or a hypothetical new built-in that would convey the meaning properly. Another problem is logical layout in SPIR-V. Formally, a model is a linear list of instructions. However, there are model and function scopes de facto, and the model scope goes in the predefined order. It's the place for type definitions, and we must reuse the same type ID for identical types. We would like to keep other definitions, like constants, unique as well to avoid bloating of the output. So now imagine a function in LLVM MIR. Instructions refer definitions within the function scope, but we remember that definitions eventually must belong to the model scope and be reused. That's one more conceptual mismatch. For constants, by the way, we don't even have a choice. They, from the very beginning, are created and duplicated outside of the backend, starting with IR translator. Our talk uses the word bridging in the title, not by chance. The backend acts as a bridge between SPIR-V and LLVM concepts. The duplication of definitions and efficient gathering of model instructions are essential. The backend can't be the bottleneck in heterogeneous computing, and now the keyword is efficient. We would like to replace the translator in compute toolchains, but it's not fair to compare absolute timings. LLC runs a lot of passes, transforms and optimizes IR and MIR, and somewhere between other passes with the backend lowers IR to SPIR-V. The Khronos tool, meanwhile, translates without LLVM overheads. So it's okay if translator is quicker. It's not okay, though, if we see that it's 560 times quicker, hence the scream. The first addressed root cause was exactly inefficient approach to gather model scope instructions. The duplication used to build a dependency graph for IDs, and the data structure didn't scale well. We removed the graph altogether, and translation time got 5 times speed up, a solid step to close the performance gap. The next step was to further improve the duplication and tracking of types and values. We reworked internal intrinsics that bloated MIR and reduced emitted pseudocodes thanks to smarter type management. Total effect is 25 times speed up from the original baseline, much cleaner intermediate state and IR/MIR dumps, and a simpler code. In future, we plan to profile memory usage and isolate and resync the type inference logic. It's currently tangled with IR transformations, complicating maintenance, so we'd like to make a standalone reusable path from type inference and probably share it between backends and other projects. Addressing performance had a side effect, expected and intended. Tracking of duplicates is not entirely trivial task because of changes in IR along the way of translation. Some changes are out of control, being a part of passes unrelated to the backend. Other changes could have been watched over, though they were not. Previous approach didn't guarantee accurate caching of entities, randomly returning stale and incorrect records due to removal of instructions and their modifications in instruction selection. So we address this problem, creating correct caching for tracing and eventual deduplication of definitions. No full control over changes in IR means a bit more complicated cache than a bidirectional mapping, although a new implementation is simpler anyway. The idea is to watch over IR changes, invalidating records, and recognizing stale items by creating a unique key from an LLVM IR entity based on type and contents, and storing a corresponding instruction with redundancy that ensures eventual consistency of the cache. Consistency is eventual because of IR changes out of the backend, and redundancy in general and custom hashing in particular helps to distinguish between valid and stale records. We store definitions as a tuple of machine instructions, its definition virtual register and hash, and along with bidirectional mapping, this is enough to provide consistent add, find, and erase operations. We reuse the record when we see a definition for this vreg in the machine function, and the definition is the same as the stored instruction. So in the past, there used to be flaky behavior in certain payloads. Now we don't observe it anymore after this fix. TableGen usage must become smarter in instruction selection, and that's our constant focus in the backend. That's a part of the backend that could use a major refactoring. We plan to give a resync to the approach and try moving manually coded semantics towards global ISL pattern matching. Now instruction selection code often looks repetitive and handleable by TableGen patterns, so there is a space for improvements. Recent achievements already include validity from the perspective of machine verifier, simplification of TableGen manually coded rules, intermediate representations, and underlying assumptions. There was a couple of problematic interactions with global ISL discussed at the latest US LLVM dev meeting. Let's revisit them briefly from a pragmatic perspective. The first is op-phi in SPIR-V, that is a phi node, but is not recognized as such. We had discussed the idea to patch LLVM code generation to allow overriding the hard-coded check in machine instruction is phi, as the opposite to patching the SPIR-V backend and postponing generation of op-phi. So wouldn't it be better to support the specified target opcode behavior after instruction selection phase? The answer appeared to be no. Overriding the hard-coded check is an elegant solution because selected instructions should not require any further selection. Target instruction info could help backends to report phi instructions in their ISA, but the problem is that the ship is long gone. Optimization passes are using the hard-coded check, and there are about 300 places to refactor. So elegant doesn't look feasible. We aligned with Codebase and used 5 generic opcode until model finalization. This enabled optimization passes for us. Similar problem, but the opposite solution. To keep operand types consistent, the backend uses bitcasts between pointers. We tried to use generic gbitcast, but the solution is to generate SPIR-V op bitcast instead. The rationale is that low-level types don't bring enough info to align usage of gbitcast with SPIR-V, so we can't emit a generic opcode. Its semantics differs from op bitcast. Back to the community aspects, the backend's evident progress and non-experimental status enabled new applications. SQL remains the main driver of changes, and new AI workloads and extensions are work in progress. New use cases bring up the issue of missing BF16 support. BF16 is important. Global ICL doesn't distinguish the semantics difference, seeing 16 bits of floating point just as an IEEE half. So this ambiguity is a problem, especially in AI workloads. We need to ensure that correct bit patterns are preserved and instructions interpret bits properly, representing non-standard floating types in global ICL accurately and providing a solid foundation for efficient codegen and mass appearance. Lack of BF16 awareness leads to workarounds in representing in global ICL. Projects use half floats or integers for encoding and then rely on intrinsics or metadata or add bitcasts. Separate register banks may complicate this, and backends need to guess if a 16-bit value is really float or integer from the context. All this fragments the ecosystem and increases the chance of errors. LLVM community proposed several options to properly represent BF16 and other non-standard floats. The first is to extend low-level type with extra bits to distinguish between variants. Another is to redefine LLT kinds, adding a field to specify formats, including future extensions like FP8 and TF32. The downside is that it requires a bigger refactoring. The next is to embed a type N operand in the floating point instructions. We would make MIR more verbose, and passes would have to pay attention to the extra operand. Finally, we could step into a reasoning territory, attaching metadata and relying on analysis pass. In sum, we really need a first-class representation of BF16 to avoid pitfalls of guessing. Our test suite is expanding rapidly, reflecting evolving priorities. Tests go beyond file check. We use SPIR-V val to ensure the code is syntactically and semantically valid. Looking ahead, we plan to identify weak spots in coverage and automate non-functional testing. Promotion of the backend called more build bots and continuous integration environments, which quickly uncovered a few fixed spots. Many of these issues were minor but still needed urgent fixes. As a broader lesson, in such big code bases as LLVM, even a diligent care about quality of the subproject can allow hard-to-detect bugs to remain unseen, resulting in surprises in new settings. The expanded coverage from build bots, sanitizers, and external environments really helps. The backend is stable in heterogeneous computing domains. We've got better support for OpenCL and addressed all known issues in SQL CTS. Pass rates are high also for Triton and SQL end-to-end test suites, with some features intentionally unsupported and other in progress. Adding extensions may require more time and efforts, as in the example of joint matrix. There is a lot of moving parts in QA. Downstream Intel LLVM, upstream LLVM, Khronos Translator, runtimes, drivers, sometimes Git branches. Components get updated on different schedules, and there is always a lag. Hence, pass rates in CI workflows can look lower than they actually are, until environments are updated to consistent state. Still, continuous testing outside of LLVM helps. We now check how runtime performance of SPIR-V code generated by the backend compares to code produced by the Khronos translator. It's at the beginning, on the stage of initial probes. A thorough and automated approach is to do. First results are good news. runtime performance of our code is on par and don't have significant difference with translator. So at the beginning of this presentation, I told you that it's a series of mini lessons rather than one message to convey. So if I were to pick up just one message now, it would be that the LLVM SPIR-V backend is a mature and stable project, and it's ready to replace Khronos Translator in toolchains. Thank you for your attention.
Hello, thanks for the presentation. Two short questions on type inference. You said that taking mangled names and their information into account is kind of dangerous. Maybe you can elaborate on that. And the other question is, do you think it's feasible to use debug information to help type inference?
It's a very good question because both mangling and debugging for should not be used for any semantic reasoning at all. So debugging for should not influence semantics, any semantics results or analysis at all. Mangling is not stable at all, absolutely. So you have no guarantees. Mangling. Basically, I know compilers that would like to proceed without mangling at all. So for example, MLIR workloads would like to avoid mangling. Mangling is our last effort, and I know just one case for the whole SPIR-V backend that requires mangling as a last effort. Actually, it was on the slide. It's about op-async copy, just because it's the only one instruction that refers to number of elements rather than number of bytes. So you just force it to use correct types, or runtime has no chance to do the right thing.
Okay, so I understand it correctly that you use it as a fallback, but it is not the proper way to go.
Yeah, absolutely. So it's a fallback. I mean, it's for such cases when IR just have no tips at all to infer types properly.
Thank you very much.
There is an open pull request to add the floating point types to LLT.
Yeah. I know, and it's in this review as well, and it would be really great to see. BF16, by the way, also use case from the real life. So I was contacted inside Intel by people who are working with XLA adoption inside Intel. So basically, it's one of things that should be resolved in upstream to make it easier in related projects.
So you said it's basically, it's pretty mature and things work. Have you looked at, for example, the Levytskyy GPU effort that compiles Levytskyy to AMD and NVIDIA GPUs natively, just enabling that for Intel GPUs and so on and so forth. So other places where we already target, accelerators. Now, I mean, you gave an Intel talk, like targeting the Intel accelerators from there through SPIR-V, or targeting the other accelerators through SPIR-V where possible. I mean, we have in upstream things that we could use this for and basically ensure ourselves that it works well. Have you looked into those?
But we're talking about native LLVM backend. So first of all, neither SPIR-V standard nor the SPIR-V backend are limited to Intel or related to Intel somehow intrinsically.
Right. But did you try out compiling the Levytskyy GPU through your backend and actually running it somewhere?
No.
Okay,
no.
Thank you.
I would like to elaborate a bit about the question. So it's absolutely not about one company because, the overall goal is to help the community in general. It's just IR vendor-independent IR and native LLVM SPIR-V backend. In theory, they are agnostic towards any vendor, so we can use it anywhere.
This will be our final question.
So is the version you have, the SPIR-V, also work with the MLIR SPIR-V, or is slightly different version?
You mean what is the relation between MLIR dialect and...
Right, MLIR now looks like has something like a SPIR-V dialect. So this is independent SPIR-V? Or?
So we have, what is SPIR-V? SPIR-V is a standard, it's a language, and we have the backend for it in LLVM project. We have dialect in MLIR, but this talk is not related to MLIR dialect. So this talk is closer to translation of LLVM IR to SPIR-V.
Okay, thank you.
Thank you.